pleasure to welcome Rakshita Joshi from the Indian Institute of Science. She is a PhD student in the Department of Mechanical Engineering there. She just submitted the thesis, part of which is on self-propulsion and pitching airfoils. Welcome her. Looking forward to it.
Yeah. Thank you. It's all audible, right? I didn't. Yeah, good afternoon, everyone. I think this is more strength my colloquium here. So, so I'll present briefly about, not very brief, but a little bit about what I did for my PhD. And it encompasses essentially self-propulsion. And I focus mainly on pitching airfoils. So today I'll first try to introduce the topic. I will spend a bit of time there just to give more of the background and make a case for why it was important to study this and what's the complexity involved in studying such problems. One of the key aspect here was, in fact, designing and building the apparatus that we used for achieving self-propulsion in the first place. Then there are three major aspects that I'll discuss in the self-propulsion itself. One is the kinematics, which is basically you could say is the speed aspect, how fast the body will travel for your given input parameters. Then we'll look at wake patterns for different parameters again. And then I'll just touch upon the energetics aspect. And there's an interesting question over how you would really even define an efficiency in such problems. Now, the first question is, of course, I always try to explain my title. So the first thing is, okay, what is self-propulsion really? So self-propulsion is basically when an object propels itself forward. It could be walking. You will find numerous examples in. It could be your vehicles. It could be birds, fishes, flights, etc. There are some bodies where you can say separate regions which say produces thrust and regions that would be experiencing resistance. For example, if you take a car, you have an engine which gives you the power and which propels it forward, and the resistance that you overcome is generally largely the friction that you feel on the tires. Aerodynamic resistance is still there, but we'll leave it for some time. But when we walk on a ground, can you really distinguish between how are we producing the thrust and what is it that we are overcoming? We are certainly doing some work even when we are walking at a constant speed. But here we can't separate out that, okay, my one leg is producing thrust or my one leg is producing drag. That doesn't happen. You can, I'll actually leave an open question for you. If you take a bicycle, it's usually the back wheel which is generating your forward force which you're pedaling. And you could say the front wheel is mostly the one that's feeling a net resistive force, and together they balance each other when you travel at a constant speed. However, there is a monocycle. If you have seen, you could see YouTube videos, and as simple as the cycle is, it's dynamically very tricky to really solve for thrust and drag, and you can't really separate us. So here we focus on a class of problems where such separation would not really be possible. So I'll go a little bit more on where the airfoil is coming into play now. Traditionally, the whole pitching airfoil studies, initially they started from studying flutter characteristics in turbine blades, but over the last, let's say 3-4 decades, the focus has been on studying flapping or pitching airfoils as an alternate to rotary thrusters, like in a fish. So this is a schematic of what biologists call as thunniform fishes, like all your sharks, dolphins, etc., which are large distance swimmer. They travel really long distance and are migratory in nature and and they travel at quite a decent speed also. And in most such fishes, the thrust is largely said to be produced by flapping of the caudal fin, and it's the frontal part of the fish body that experiences the drag. So that way, if one can develop a flapping thruster, we could see how it would be beneficial in using, in designing, let's say, or underwater vehicles, etc. So that was the motivation in studying pitching airfoils uh, for as a alternate to rotary propellers. So now the cross section of the caudal fin of a fish has a symmetric airfoil cross section, and when it actually just oscillates in general, you could take the motion together as a combined heave and pitch motion of the fin. So if you just take a simple symmetric airfoil section and allow it to heave and pitch or pitch, then you could then you would be generating thrust at some parameter. And there's been a lot of studies focusing on how much is the thrust produced, when is the efficiency maximum, etc. However, even this simple airfoil model, uh, before it starts producing net thrust, experiences net drag. So what do I mean by that? So here I have a net thrust measured on a pitching airfoil. So it's an airfoil like this. They've removed the heave aspect, just the pitch, that's the theta component is present, and there is a uniform free stream that it is subjected to. And these dots, all the pointers over there correspond to the measured forces at different amplitudes. And the x-axis is what is called as reduced frequency, which we will also be using a little bit, that characterizes the unsteadiness and also takes into account the frequency at which the airfoil is being pitched. So so when it is not being pitched, that's when it's in a steady state, a symmetric airfoil, of course, experiences drag. As you go on increasing the frequency, it is still in a net drag producing region, but that net drag slowly decreases, and then it crosses over and starts producing net thrust. So here, if you follow the black solid dots, you can see roughly at about K little more than 10, it crosses over into a net thrust producing body. So even this simple airfoil model is coming across this. The point of interest for me now is that net thrust equal to 0 region, where I can say it is self-propelling, because when the airfoil is also pitching airfoil is also an object which is experiencing a drag and also generating thrust at the same time. So we take pitching airfoil as a model object to study self-propulsion characteristics in such bodies.
Pitching is about some fish pond.
Yeah, generally about 1/3 chord length. 1/3. For this, this is the data I've taken from Minkowski and Williamson's. So here they pitch it at about quarter chord from the leading edge. So it does matter where you pitch, but given you take a constant pitching point, then you roughly get this. No, this is just me providing a motivation, saying that even a simple airfoil, which is pitching, and as you go on increasing the frequency, it does transition from a net drag producing to net thrust producing. So it does give us that region we want where the net force is 0. So when
What are the two curves here?
they are just at different amplitude. So this is a validation curve which they had published. One is for they compared it with different experimental work, which is the top one, and the bottom one is the direct thrust measurement, and the first upper sharper curve is deriving the thrust coefficient from wake measurements. So that's a later and perhaps a tangential argument why you would not exactly get the thrust values from wake measurements. You have to account for fluctuations which give rise to pressure deficits, etc. So the solid black dots, they are direct force measurements. Yes, it makes a difference. So there is an optimal phase difference that leads to efficient propulsion. But for everything that I'm going to talk today, I'm not doing heaving at all. We are giving only pitching motion. The reason we also stick with pitching motion is uh, the airfoil is pitching, the net lift, aerodynamic lift on the, let's say, how do you call it? I don't know what component you would want to call it, but let's say if you have an airfoil at a certain angle of attack to your incoming flow, there'll be a certain lift force on the airfoil. So because this is continuously changing its angle, it will have an unsteady lift. But the average contribution of this lift to the thrust would be zero because it goes in one direction on one half and in the other direction in the other half. So the net contribution of the lift in pitching the shouldn't call it really lift because there are many other components coming to it, but just this quasi-steady lift would be zero. But that won't be the case in heaving. So it, in a way, helps us eliminate that contribution and look at different other contributions that may be at play. I'll come to that a bit at a later stage. So here's another example of a work done by one of my senior at IISc, Anil Das. This was a numerical study where they pitch the airfoil and also allow it to propel and achieve whatever steady speed it wants to achieve. In the earlier example, uh, which I gave here these were experiments were done in a water tunnel where the flow speed was constant. So you are just going on increasing the frequency and coming to a point where the net thrust is zero. Now here, on the contrary, we just allow it to propel. So a propelling, so an airfoil which is propelling on its own would start from rest, gradually increase, the speed would gradually increase and it will reach sort of a steady state, quasi-steady in a way, sense, where the net thrust is balanced by the net drag that it experiences. So this was also one study which does show that oscillating airfoils exhibit an ability to self-propel. And this was a 2D simulation.
Earlier graph, the pitching airfoil was not allowed to move.
No, it was just pitched in a water tunnel and you have a uniform free stream. So for a given velocity and given input, you'll find one particular frequency for a given amplitude where that net force is going to be zero. So if you really want to find out what speed it is, you are going to have to do that experiment for a very large number of, you have to keep changing the tunnel speed, which is quite not practical actually, because they're built to be operated in a range.
But if it's allowed to move like in this
Yes.
simulation, and if you make the curve like your previous slide,
Huh?
would that 0 point move to the right or to the left? Let's say you have oscillating
Yeah.
airfoil that's allowed to move.
Yeah, so we will see further how frequency will affect. That is my prime objective. Now to see, now that we know that oscillating airfoils do self-propel, the next question is how are my input parameters, which is frequency, amplitude, and even the pitching point location, that is going to affect the speed that it will attain. And it will move to the right. So, this essentially was just to lay the ground for understanding why we are even interested in self-propulsion in the first place. One is, of course, like I said, the whole motivation behind studying even oscillating airfoils was to design underwater vehicles. But even in underwater vehicles, and let's say even the whole assumption of spatial separation of your drag and thrust is valid, there's always an interaction between these two bodies, and it's difficult to take the thrust characteristics and then just correlate it with the drag characteristics. So one does need to look at how it really works when it is self-propelling. And second, there has been no experimental database on self-propulsion so far, But with the advancement of numerical techniques, especially like the immerse boundary methods, which are able to handle moving boundaries, there has been a slight increase in the number of studies, numerical studies in self-propulsion. However, at least I have been working on this for over a decade right now, and we have not seen any experimental work just on self-propulsion. There have been work on thrust measurements, but not on self-propulsion. So, of course, I've been giving the motivation always that one possible application is definitely all the underwater vehicles, and that serves as a motivation for everybody who's trying to understand and build robotic fishes. But I came across an interesting application that say that such vehicles could be used for exploring dense environments like that of Venus's atmosphere, which is a lot dense compared to Earth or Mars for that matter. It's not as same as water, but it's quite dense. So flapping, this oscillating kind of mechanism works quite well, apparently, for that. I can give a reference later if you are interested. Then the next major question is, how do we achieve self-propulsion? I explained earlier, and I was also discussing that if you have a water tunnel, or you could use a wind tunnel, but water tunnels would be better, and you just say pitch an airfoil at a given frequency or amplitude, then you would have to keep tuning your wind tunnel speed to come to a point where the net force on the body is zero. Now imagine having to do this for about 80 different parameters and not knowing what the range of speeds that you might be getting. So that way, directly achieving self-propulsion like the numerical simulation seems much more lucrative, in the sense you have an easy control over the parameters, and you're and if you're able to just measure what end speed it reaches, you're happy because that's what you're really interested in. Now, if you want to achieve self-propulsion directly, then you will need at least one unconstrained degree of freedom. What does that mean? That it should be able to move freely in at least one direction. So then what we are interested in is what speed it will achieve if it generates enough thrust to overcome the drag that the airfoil only experiences. So you do not want any friction coming from your supporting structures, because they are definitely going to offset whatever drag it is, whatever thrust it is producing. Then we are also interested in seeing how the flow field is, that is how the wake is, how it evolves and how it changes across different parameters. So you do not want to go in a round kind of a scenario. Now I'll come to why I'm telling round. So you want to, so if you have a large inertia of a system, then it has to travel a very long distance to achieve a steady state. So lower inertia means you can achieve that steady state fairly quickly. Now, in my work, I have used a rotary setup. I'll come something like this, where one more need is that it needs to have a very long arm, which is represented by this truss kind of crisscross structure. So why we need a long arm? Because we want to still negate all the centrifugal and centripetal effects and still be able to approximate the motion as linear. So the apparatus that we built, it has this is a carbon fiber truss like structure, and it's very light actually. It's about 20-30 grams, and it can actually take a huge amount of it, and it's about 1 meter length. The airfoil is at one end here. It has about 4 centimeter cord, and it is actuated by a mechanism. So this is the driving motor here, and this motor with a mechanism is used to actuate the airfoil here sinusoidally. And to satisfy the frictionless criteria, what we use is air bearings. So air bearings are basically aerodynamic version of your hydrodynamic bearings, where the working fluid is high pressure air. So the dynamic friction of these air bearings is much smaller compared to the thrust values that we are looking at. And the rotation or the position measurement here, I do it by using a rotary encoder. So once the airfoil is pitched in let's say in this plane, it will start to propel and follow this sort of curved path across the entire water tunnel. Here again, it's not measure, but this sorry, not water tunnel, water tank. This is about the tank is about 2 meter in length and 1 meter wide. And the rotary encoder, which is used to measure the rotation of the arm, can then be used to calculate the linear position of the airfoil. A simple measurement. So now how do we know what exactly is the self-propulsion speed here, or how do we report it? So if you plot the position of this airfoil with respect to time, it starts from rest, shows there is an acceleration, and then it reaches a region where position increases linearly with time. So it's a simple kinematics here, and if you fit a linear curve in this region, the slope of that region should be able to give you the speed. So in the entire study and all the results that I will discuss here, the self-propulsion speed is obtained this way across many trials. So this is example of just one trial, and in one trial you will, depending on the parameters, you may be covering about 4 to 6 oscillations. That way we cover at least 15 to 20 different trials. So every self-propulsion speed value that we report and discuss is averaged over, let's say, about 150 oscillation cycles. Yeah, we don't start very close to the walls. Move away a bit, at least 3 to 4 chord lengths, and then start and stop before it reaches the next boundary. And because it's traveling in a curved path, it does give an advantage that you're still able to get a 2 meter path length without, despite neglecting the boundaries.
What about the drag acting on the arm?
Yeah, so we did try to quantify the drag that will come on. One is this one. Yeah. So the airfoils. So one is this is kind of, it has a lot of gaps. It's not one solid. It's not a solid bar like this. It's a truss. So it has a lot of air gap in between. And I have tried to measure that resistance also. It's much less compared to the drag. I even tried to estimate the drag on this shaft, which was actually more crucial than this one. So with both of them, um, so here what I did was a very controlled experiment in which I changed the depth uh, up to which this shaft is exposed. So that basically changes the amount of resistance force that's coming from the cylinder. And then you kind of extrapolate it to go to zero and try to minimize it. And then see how much is the variation in the self-propulsion speed. So that variation was within the error bars of the speed measure that we were getting. So it was, you could say, negligible. And the parameters that I studied, let's say, for example, the frequency, we start from a small frequency in which we can see propulsion, because even at a very small frequency, sometimes these there may, I don't know, sometimes it does propels very slow or it does not propel at all. So we start from a frequency where we can get reasonably repeatable self-propulsion and end at a frequency where we start to see surface waves or oscillations, because they again start to induce drag and other effects which we don't want to get into. We still want a very clean surface to work with. So all the measurements are in that region. So here is just a simple sketch of the mechanism that I said, which is used to actuate the airfoil. So this is essentially a planar crank rocker mechanism, which we all study in BTech. So there's a motor crank which is rotating, and it is connected to a rocker which is oscillating. And the ratio between the radius of this crank to the radius of this arm is what decides your amplitude of pitching, and the frequency is essentially just the rotational frequency of the motor itself. This is a very simple kinematic relation one can derive, and we use a power spring here to ensure that there's a sustained motion. So here we just tested the mechanism for different loading conditions, that is different frequencies and different weights also attached to it, uh, for different design amplitudes. And these are the amplitudes which I'll roughly studied throughout. And we get a fairly satisfactory sinusoidal motion. Right. So the models that we have used in this study is one, a rigid airfoil, which is a NACA symmetric airfoil section. It's just a small one, has 4 centimeters the chord. It's about 10 centimeter long. And it's pitched at a certain distance from the leading edge, which itself is a variable. Then the next part, I also try to explore what is the effect of flexibility by using a composite foil in which I essentially attach a flexible flap to the end of this airfoil. And this flexible flap is a simple OHP sheet of 100 micron. Okay. So for the rigid airfoil, what I vary is the pitching point. It's essentially how far it is from the leading edge. So P1 corresponds to a distance of something like 0.125 chord length. It's quite close to the leading edge. P3 is about 1/3 chord. P2 is about 1/3 chord, and P3 is very close to the mid position. And the amplitudes which we vary, I represent it as A1, A2, A3, and A4 in all the figures. And for roughly, one could take it as 5, 10, 15, 20 degrees. It's not exactly that value, but that works just for understanding. There's a large range of frequencies I work with, and as I explained earlier, it's limited by when the propulsion starts and stops at a point where we start to see surface sloshing and waves. So with all this, the question we're trying to answer is how they imposed kinematics. So there were 3 imposed kinematics: pitching point location, amplitude of pitching, and frequency of pitching. How they affect the speed? How do they affect the efficiency? And third, and most important perhaps, is what is the role of flexibility? Because what we see in nature are flexible. Somehow we don't find flexible structures in engineered ones. So the kinematics aspect, that's the speed. Let's see how they change. So in rigid airfoils, we classify this speed relation into 3 different scaling regimes, and across all the parameters, they fall and fit into these scaling regimes. So I'll go a bit Arabic in my style and go from right to left. So in the right side, what I have is is RES. RES is essentially a self-propulsion Reynolds number, basically defined based on the self-propulsion speed. And I'm plotting it against something called RETE, which is a trailing edge Reynolds number. So what this trailing edge Reynolds number is, it's taking into account the frequency of pitching, which gives me a time scale, and it is also taking into account something here called A. A is oh my god. So A here is the total trailing edge excursion that the airfoil makes. I was just going to sketch it. So if I have this airfoil pitching with an angle amplitude of theta naught, then the maximum distance that this trailing edge covers, I want to represent it here. This gives me a way of accounting for theta as well and giving it some length scale. So I can define REDE based on F and A. Now with that, I'm able to club my input parameters frequency and amplitude into one. So this right side plot here, where I have all yellow points, and it says P3, which is pitching very close to the midpoint. What we see is that there's a linear relationship between the self-propulsion Reynolds number and the trailing edge Reynolds number, and it also shows the existence of a threshold below which the airfoil does not propel. Then Uh, here, the first two curves here correspond to the first two pitching points, where one was very close to the leading edge and the other was about 1/3 chord. So the red points correspond to P1, which is very close to the leading edge, and the green points correspond to 1/3. Let's say it's also not very far from the leading edge. So in the first curve here, this corresponds to pitching at low amplitude, which is close to 5 degrees. Here, what we observe is that this self-propulsion Reynolds number uh, varies with RETE to the power 3 by 2 and is also affected by the pitching point location, and it comes as a factor of 1 minus 2p. Whereas for higher amplitudes, which is 10, 15, 20 degrees, the relation is slightly different, where you have RES going actually as RETE, but multiplied by this, but divided by this A by square root of A by C. And again, there's a factor of square root of 1 minus 2p, which accounts for the pitching point location. Now, now these are purely from observations. The next, I'll make an attempt to try and explain what is the source, what could be the possible source of these scaling relations. Yeah, close to. Yeah, 0.5 C. So if you take C is the chord length, then 0.5 C is very close to the center.
We have symmetrical spheres. Then I would expect that also symmetry.
Yeah, but there are, so there was a very interesting and important paper by a group of Professor Stephen Childress, where they heaved a flat plate, basically. That's also quite symmetric. There's no asymmetry in it, but that also showed a relation which is very similar to this last curve, RES versus RETE. That beyond a threshold uh, of your giving Reynolds number, there was a spontaneous propulsion observed. Now they attribute it to some kind of, I have till date not found a concrete explanation, but they do attribute it to some kind of symmetry breaking, which is something similar which also happens here. So here we are not heaving, but we are pitching. So even when we are pitching, we do see small vortices at the leading edge and the trailing edge, which are symmetric as we are pitching. So self-propulsion happens when that symmetry breaks. Did that answer?
I was just wondering why is it exactly 1 by 2?
Yeah, yeah, I will come to that. That's a question I hope people ask me, but nobody really asks me. Uh, yeah, so I'll explain the slide and then I'll come to answering your question as to why that 1 minus 2p comes in. So we're here to understand about the scaling, or to make some physical argument about the scaling relation. Uh, I will go back to the classic problem of thrust being produced by a pitching airfoil in a uniform free stream, and try to explain, and there's proof also, that this thrust generation is essentially an inviscid phenomenon. So here, although there's no spatial separation of thrust and drag, there's a possibility that you could have different mechanisms contributing to thrust and drag. So if you go back to that problem and just see the net thrust on that pitching airfoil, I'm not talking about average, the instantaneous thrust on that on a pitching airfoil in a uniform free stream can be decomposed into an average component plus an unsteady component. Okay, so this it's a very good paper by McCoskey and Williamson where they measured this direct forces. What they did was they tried to also measure this thrust amplitude for different frequencies and angles. So all the data points that I have plotted in these curves correspond to their experimental report. It's what they have reported in the paper. So if I compare this thrust amplitude from measurement to something called as a linear inviscid theory, which was presented long ago in 1937 by Garrick. This was when NACA was at full bloom and they were constantly studying airfoils and everything in and about airfoils. If I compare these thrust amplitude values to the thrust that is derived theoretically from the inviscid theory, I see that there is a very decent match. And it also matches in even this phase angle that is predicted by the theory and the one which is reported by these experiments also have a very good match. So now what exactly is this theory taking into account? In a very simple words, because it's linear, again it's easy to separate out the components. The net inviscid thrust, according to the inviscid theory, could be decomposed into three components. One, Ct and the subscript R denotes a reactive thrust component. Then the second here is the lift. Now there are two lift contributions to it. One is the quasi-steady lift due to non-zero angle of attack, and another is the lift due to vorticity in the wake. You can take that into account. And then there will be a third contribution due to leading edge suction. So, however, in all of these, if I just separate out the reactive thrust component, then I get an expression where I have 1 minus 2p by 2, k square was the reduced frequency, and then an unsteady component. So in these curves, what I have compared, the red line here, corresponds to this expression, which is the amplitude of the reactive component of the thrust. And surprisingly, the total inviscid force, the reactive force, and the observed measured thrust amplitudes are quite coincidental. And so is true with the phase. So this gives us an impetus or insight into saying that okay, the thrust generation seems to be primarily inviscid, and among the different inviscid contributions, it's largely just coming from reactive forces. Yes. So if I take the net thrust that is given by the reactive forces, and if and because inviscid theory doesn't never talks about any kind of drag, and if I'm able to get an appropriate drag model, then for thrust generation it will give me some net thrust, but for my self propulsion this net thrust would be zero, and an appropriate drag model should be able to reproduce the same scaling relation. So now coming back to your question of why 1 minus 2p. Uh, so as I said, there's a reactive thrust component which is dominant. So I'll just draw a flat plate instead of an airfoil. So if you have a flat plate which is, let's say, pitching at a distance p from the leading edge. Let's say it is uh, doing a counterclockwise motion. So this part of the airfoil is going up and this is sort of coming down. This is, I don't know if it's hand waving, but it's some kind of explanation to understand reactive force. So because this part is coming, the reactive force on this side of the airfoil would be in this direction, normal to the airfoil, but slightly upward. And the reactive force on this part would be downward. So, starting from this pitching point and coming to a point with whose length would be equal to p. Now, this is a volumetric, but we can take infinite span. Then, this region, so the net thrust is coming from this region, with, whose length is proportional to 1 minus 2p, but a part of it also has to compensate for this opposing reactive force. So that's where we get another minus p. Does that, was I able to explain that? You will answer the question.
Yeah, I just understand approximately because p equals a half means the
Force would be
target
zero.
can go in the left or right. So
Sorry?
you put a p equal to half. You start off.
Yeah.
If you have a symmetry, then you can choose the direction of propagation. It is the left or right. But I mean, what they airfoil is not the left right.
No, because I think it is asymmetric. It doesn't propagate in any direction. It always goes in the leading edge direction. It doesn't have a fore. It's asymmetric. It doesn't have a fore and aft symmetry. Yeah. So from this, if we from this, we can, let's say, try to make an attempt to derive the scaling relations. So if I take the average thrust coming from reactive contribution, and let's take skin friction drag to be the dominant resistance for small angles, but enhanced because of moving boundaries. So moving boundary means thinner boundary layer, which would mean an enhanced skin friction. So this was actually studied very much in detail by a French group. And this is roughly the relation that they come up with, that your regular skin friction normally goes as 1 over square root of Re, but it is enhanced by a factor which is proportional to square root of Stroll number or reduced frequency into the angle. So if you balance these two, if this reactive thrust coming balances the enhanced skin friction, then it does result in a scaling relation, which is what we observe in the experiments. So there are here, just for sake of completion, I've also just put in perspective some different scaling relations that were reported by other studies in literature. So most people don't try to give an argument of the source of these scalings, but they've just reported it based on the best fit possible. Then for the second scaling region, which we saw, I called it separable scaling, if instead of skin friction, the net dominant resistance was some form of a form drag or a pressure drag, then it would scale as theta naught. That is, a pressure would act on the projected area of the airfoil, and that projected area is just proportional to your amplitude. So that results in a scaling relation, which we actually observe for the separable scaling. However, for the linear scaling, we cannot go with both of these arguments. Now, assuming the thrust is still inviscid, the major component is now no longer reactive. It could be coming from a different source. But linear theory tells us that when you're pitching very close to the midpoint, leading edge suction becomes a prominent contributor. Now, if that is still true, then one can do a back calculation and derive that this could be the form of the drag, but we do not know. This is a sort of an anomalous case where I don't really think an average thrust drag argument would be even valid to make in the first place. But just to complete it, and for the sake of completion, I would say that it's possible that there could be an average form drag which is enhanced by the unsteadiness as a KS value. Now, this is just one more way of reporting the same scaling relation, but in terms of what I call as U star BL, which is speed in terms of body length per oscillation. I use this parameter because in all fish physiology studies where they report speed of actual fishes, this is a very strong parameter. That's how they compare how different fishes travel, how different species of fishes travel. And what it does highlight is this is essentially the same speed relation recast in different form. That we see that U star BL is highest when we are close for these red points, which corresponds to P1, which corresponds to pitching very close to the leading edge. Then here, the effect of amplitude and frequency also becomes very clear. That that as you increase amplitude, speed would still increase linearly as characterized by this UBL, but speed would increase as a square root of amplitude, which means that increasing the amplitude will have less effect on your increase in. What is this happening? It is still running. No, I don't have an issue with my battery.
No, I think it's the screen. Can you just turn on the screen, the power button? Can you disconnect it? It's coming.
Yeah. But like I said, this helps us to derive better conclusions in some way. So yeah, the first point I said was as you pitch closer to the leading edge, you have higher speeds. Then increase in the frequency and amplitude, especially in the separable region, do not have uniform contribution. So you don't gain much from increasing amplitude as much as you would gain from increasing the frequency, as seen here by the square root relation. And the second thing we see is because now we have recast the relation in terms of U star BL, in the separable and the linear region, we don't see any RE actually coming into play. And if you also recall earlier, here in the second and the third scaling relation, there's a linear RE relation where your viscosity effect essentially cancels out. So that's also interesting to see that it's only at low amplitude, close to leading edge pitching, that you have some effect of effect of viscosity coming into play, as there's a skin friction being dominant. But in the other two and higher amplitude scaling, you do not see any dependence on viscosity at all. Now, so how are we doing with time? I'll go ahead based on that. So the next thing I think I tried to say in my objectives was what happens when we introduce flexibility. So here I tried to compare the Reynolds number relation for composite airfoil for the similar set of input parameters. Now, instead of RETE and REF are essentially very similar parameters. So your RETE was defined based on this A, but for composite, because there is a clap, it will actually bend and the actual A is quite different. However, if I assume this flap to be just a rigid extension, then I will get an amplitude which I call as RF, which essentially means rigid flap. That's what we take to parameterize and make a comparison with the rigid. Otherwise, it won't compare them. So it's in loose terms, they are pretty similar and same. So here in the inset, what I have is the RES comparison for the power scaling relation, which we saw in the for rigid airfoils. And for the sake of clarity, I'm comparing it only with the one pitching point here, which was closest to the leading edge, and that was the fastest, and also because the pitching point of composite and the rigid airfoil is comparable only with P1, not with the rest of it. So that's enough to draw useful conclusions. Otherwise, it will just be clustered with too many points. So here we see that low amplitude, there's a very large deviation from the rigid airfoil scaling. However, for larger amplitudes, the composite airfoil behaves or the speed very closely follows the rigid airfoil relation except at these large RET or REF where it starts to deviate. So the deviation is slightly early for A2, but the deviation is at much slightly higher REF for other amplitude. So one can try to understand the source of deviation by trying to see how this flap deflection really happens when the airfoil is propeller. So this flap deflection can be quantified as what is the maximum amplitude that this flap tip would move, and what is the phase difference between the flap tip and the airfoil trailing edge. So if it was a rigid extension, then there would be no phase difference at all. So higher phase difference would mean the effect of flexibility being stronger. So here I do not take or try to define any other parameter, but just work with this phase difference as being a parameter which accounts for flexibility in a way. Here I see an example of airfoil at low amplitude but at frequency 1, 3 and 6 hertz. And here is basically a plot of the black line corresponds to the airfoil trailing edge while the blue line corresponds to the flap tip. So what we see here is that the change in different bending shape as we increase the frequency, and also the increasing phase shift between the trailing edge and airfoil trailing edge and the flap tip. So now here I plot it for almost the parameters for which we could extract them and see that the lower amplitude case is the one where I see very large phase differences, and this is the one that deviated maximum from the rigid airfoil behavior. Whereas for higher amplitudes, the phase difference does not cross even 90 degrees to in some cases. And only when it reaches this maximum is perhaps when we start to see the deviation from the rigid airfoil behavior. All right. So there is a bit, there's quite a lot more, but I will wrap up with the flow pattern here because it's just quite a few images and they're quite interesting to see. And it sets the ground for a very important question that if attaching flexible flap is not doing much to the speed, we didn't see a very drastic increase in speed compared to the rigid airfoil, whereas there was a small deviation, but also slightly smaller speeds, in fact, once you have attached the flexible flap. So you're definitely not gaining much in terms of speed. Then what's the point of including flexibility? What is it really doing? And But we also see that in actual fishes and in real scenarios, flexibility is present. So it means that it needs to do something over there. So for that, we try to see what are the flow patterns in the wake and get an understanding. Generally, for self-propelling airfoils, and it's also true for thrust-producing airfoil, that the vorticity from the bottom rolls up into, let's say, a counterclockwise vortex, and it is shed on the top half of the chord line, whereas the vorticity from the top part rolls up into a clockwise vortex, and it is shed into the bottom half of the chord line. This results in an average profile which is jet-like, and compared, and we call it a reverse Kármán vortex tree, whereas in the traditional drag producing Kármán vortex tree, this bottom vorticity will stay in the bottom side of your center line and the top vorticity stays at the top of the center line. However, you might, it's a different discussion later, but even in self-propelling bodies, we see pattern very similar to reverse Kármán, but this vertical separation between the vortices is very small. They are quite largely along the center line. So for rigid airfoil, we see different types of patterns. However, all the patterns are discernible just very close to the airfoil. A common feature in rigid airfoil is this really wide, unsteady, and perhaps three-dimensional wake. This is split, yes. So this is an example of deflecting vortex pairs where the vorticity shed from top and bottom are, let's say the horizontal distance between the two vortices depends on how fast the airfoil is moving. So in this low amplitude and low speed case, the airfoil hasn't moved much in one oscillation. So you have shed let's say a clockwise vortex, then there is a counterclockwise vortex shed in an immediate vicinity. These two vortices are quite close enough that they interact, and two counteracting vortices tend to deflect, and that's what we see here.
Sorry, why did you say it's three-dimensional?
I see it in the PIV also. One is, okay, there are three quantitative suggestions to make that assessment. One, there's a rapid change in the divergence. Then even, I'll not cover it now, but even if you take the momentum flux, kinetic energy flux, there's a rapid dip once this region starts. And even in the flow field, if you see, you'll start to see sources and sink. So although all my measurements are in mid-plane, and we do take whatever we get in the mid-plane, but it does become slightly three-dimensional. Then the second pattern which we can see is this reverse Kármán, which I explained earlier. Now the airfoil is fast enough so that the shed vortices are not that close enough to interact or deflect, and they more or less stay on the center line. But again, the pattern is still highly unstable, and again we see sort of a wider wake. Then a third pattern which you could slightly distinguish from the reverse Kármán is that instead of one large vortex being shed, the vortex shedding happens in a series of, that there will be a large vortex, but there are also successive smaller vortices that are being shed. And as the speed increases, as the self-propelling speed increases, you would see more such smaller vortices. So one can actually map these patterns. Now again, all these patterns are visible only in perhaps one chord length downstream, and as I said, it is it's quite dependent on the speed, self-propulsion speed, as characterized by U star BL. So for low speed, you would get a deflected vortex pair. Moderate speed, sort of moderate amplitudes, you would get a reverse Kármán. But anything higher than that, you would have it mostly reverse Kármán, but again smaller vortices which coalesce into or merge into a larger one. These patterns are visible and observed for rigid airfoil. However, For composite airfoil, this is the low amplitude case where, firstly, the wake is very narrow. It was very wide in case of rigid. Now suddenly it's become very narrow. Then the shed vortices are stable, at least for a much longer period. And no, I wouldn't be showing it, but we see in PIV that this field is a lot more two-dimensional. That your divergence is fairly constant, fluxes are fairly constant, and there's very less or minimal out of plane motion that we see in case of composite airfoil. Let me just show you this. And you closely observe the vortices are also spaced quite closely to the center line. So the further apart they are, means they carry more momentum. So with increase in amplitude and frequency, what happens in composite airfoils is it still retains a narrowness in the structure, but instead of one large vortex being shed, the vorticity actually sheds as a sheet, which is unstable, and you find these small vortices, which is some sort of Kelvin-Helmholtz instability. That's what many people say. And these small vortices start to merge and form larger vortices. But um, further downstream, these also tend to interact with each other. But an interesting and very important change that happens the moment you attach a flap is that your flow field has become very narrow, which means you're not losing out the momentum in lateral direction, but you're kind of redirecting it in the direction of your propulsion. So I would probably just conclude at this. And so what we do in PIV is essentially try to quantify this. What I gave you is a qualitative picture of how wake looks like. By through PIV, we try to quantify what is the average kinetic energy flux and the kinetic energy. You could simply try to understand it as lesser the disturbance in the wake, less will be the energy that you're kind of wasting to achieve a certain speed. So what is happening when you attach a flexible flap? It is uh, anything that goes in the normal direction is kind of wasted. So it's kind of redirecting the momentum and energy from the normal to the propulsion direction, which makes composite airfoils more efficient in propulsion than compared to rigid airfoils. So, if I have to sum up the entire work in one sentence or two maybe, then it would be that rigid airfoils do exhibit different scaling or different relations in terms of how the speed is affected by input kinematics, and you would get much faster propelling airfoils if you pitch close to the leading edge. However, by attaching a flexibility flap or by introducing flexibility, you do not gain much in terms of kinematics, that is, there's no appreciable increase in the speed. However, it alters the flow field and how the momentum and energy are directed, which leads to efficient propulsion and somewhere starts to explain why fishes are flexible. Thank you.
If you have a measure of the power consumed by the system,
No, I tried it, but there was a lot of noise, and also the airfoil is actuated through a power spring. The dissipation in that spring and the friction with the spring and the holder were making it very difficult to just obtain that. So no, I have not. That would have been a direct way, but there are two challenges to it. One is this friction coming from the mechanism, etc. And the second, which perhaps I did not mention earlier, is in the apparatus, the motor is powered by a set of batteries, and the controller is pre-programmed, and there is a microcontroller which helps me change, gives a different speed of pulse width modulated signal for different frequencies. All of that I mount on the airfoil, on this truss itself. Because imagine I'm going for almost a negligible friction setup. So any wire that I'm taking out of the system, and it actually took us some time to do that, because even a small wire that you're taking out of the system is going to contribute to some torque, and there'll be tension in that. So because you have to put everything on board, it also makes this live tracking much more difficult. I don't think it's impossible because we have a controller on board, but it would have been a lot more challenging.
What's the point of the back? The typical not from the TPC, or is there something?
What do you mean by back?
Like,
Trailing edge.
TPC, I think it's
Trailing edge or leading edge?
let's
Trailing
say
edge.
trailing edge, I mean,
I would like to think that something opposite might happen, because if you have reactive force to be majorly contributing, then what's happening on the leading edge half of the airfoil is pretty much what should happen on the trailing edge, except that you will start to propel in a trailing edge first direction. That is what I think, but I do not know because there's a fore and aft asymmetry. There is an extent to which I can extend flat plate arguments, but I really do not know. It could be very similar, but I'll still give room for not being similar.
Any other questions?
what is the length of the lap?
Yeah, the flap I have used is about 3/4, 3/4 C, so 0.75 C.
So while it is lapping, do you see what is happening?
Unfortunately, no, not with this material and this length. So here what I have used is a OHP sheet and of about 0.75 C. Here I think I just see one and perhaps sometimes going to the second mode, but I don't see any higher modes. However, before I even built the air bearing setup, I had earlier built one using ball bearings, but that had different challenges altogether. But that time I was working with using filter papers as a flap material, and I had changed the lengths. In the sense, I went from something like 0.25 C to almost about 2 C. So you have a very long flap. So I definitely saw observed a lot of higher modes. So that this is actually something I do plan to do now, that I have used only a single material. So one way of getting higher mode would be either to increase the length, but that brings more challenges in the sense the entire setup is again based on the fact that I don't want centrifugal effects or curvature effects coming in, and you don't want to change the aspect ratio too much also. So one way which I feel can higher modes can be explored is by using material that is a lot more flimsy. So that's something I would do.
So you have you concluded with that at the part that using flexible part, you are getting not that much increase in speed,
Efficiency.
efficiency,
Yeah.
the momentum and kinetic
Yeah.
sensation around that. So what do you think? Where this like without in the rigid body, the waves were like
Wider.
and in that, so like, is there any like where is this energy actually where there is not that much?
Yeah, so I think my understanding is that so what happens in composite airfoil is, especially this, even if you look at the phase difference diagram, this there may be small phase difference, but there's always a phase difference, which means that this it's a exaggerated picture, but this is often what is happening. So even if the airfoil has pitched up or it's in this upward motion, this flexible flap is still directing it towards the loop forward. So what the flow which would have been shed, or the vorticity which would have been shed somewhere here or at this point, is now being redirected along That's again, I don't know how concrete that explanation is, but it's kind of instead of it going like yeah, instead of this vorticity being released here, this is still being brought along, and this bending itself is a response again to the motion. So how well or how much efficiently it is. So I didn't give you much in terms of a comparison between different amplitudes in the composite airfoil. But the larger is the phase difference, and there's actually one seems to be an optimal. I'm not hitting. I'm hitting a point where I get something, but I have just one data point, which I'm not able to conclude that. But there is a possibility that there is an optimal phase difference at which that redirection is most efficient. So you cannot redirect it completely on the second. One way of thinking would be that you do not want this momentum and energy to be put too much in the second half of the chord line, but you do not want it somewhere here also. So if you're able to just redirect it along as much as along the chord line, you are at the most efficient.
Is there any other you have the flexibility?
Yeah, I think that again
What
would.
is the next step?
Yeah, the next step, like I said, I wanted to change the materials, and that way you can characterize the material property and see which material gives you faster and which gives you more efficient. And I have a feeling that faster and more efficient will be two different.
Any other questions?
Say, for the techniques to increase the degree of freedom, how is let's say on within XR or that we have normal components of the equipment. If you extend your freedom, does it count that making decision?
I would, yeah. So actually, this is something that I mentioned Anil Das's work, who was my senior. So he all in his numerical work, he also went for the next degree of freedom, where actually even the normal forces are quite strong. When you allow it to propel only in the longitudinal direction, you are looking just at the longitudinal components, but normal components are also quite strong. So it does go into an induced heave, and it does. However, the wake behavior in rigid airfoil, what they reported, was not very different from that of the rigid airfoil. And there is also argument that your combined heaving and pitching can be, in a way, understood to be pitching at a certain point, but I don't really agree with that. Coming to your question of whether when you allow an induced heave and then have a flexibility attached, would the argument that flexibility leads to more efficient propulsion be still valid? I do believe that it might still be valid because uh, your there is no lag in the response of the rigid airfoil to an up and down motion, whereas there will be a certain lag coming on the flexible part. So if you're moving it with a certain time scale or certain speed, this will respond immediately, but this will take some time to respond to that. That could contribute. Um, and another, I do not know how to even comprehend the normal forces when you have heaving, because it's very easy to on a rigid airfoil to say okay, it is normal to the chord line, but when you have a flexible component, the force on it is a result of the motion, and the motion is a result of the force. So yeah, I actually cannot comprehend whether it will still be like, it can counteract the normal force on the rigid airfoil itself. So how it might behave as a whole is something I'm not very sure of. So it's possible that this is moving, making an upward motion, and this is probably still doing some rotation as well as something else. So I don't know. So, but I still feel that it might contribute to how much? I don't know, but it might still lead to a more efficient propulsion. That argument I would still stand by, unless proven otherwise.
Okay, let's thank Rakshita.
Thank you.